All right, lesson number 23, posted May 29th. This is, we'll continue on with buffers, and then we're going to move on to titration. This is all about neutralization, when we have an acid and a base coming together. All right, so this is posted on May 29th. If you're watching on that day, we have a review on that. Homework number 21 is due tonight. Test 3 is on June 1st. That's Monday, June 1st. Homework for this lesson, it's not due in a week. It's actually due a little bit shorter. It's due on Wednesday, June 3rd, right? Everything gets a little more compacted in this, okay? So homework number 23 on Sapling, Wednesday, June 3rd at midnight. All right, and then a week after that is our final, right? We're getting towards the end. Stay strong. Let's finish up this in a good place. All right, so a review of last time. Last time we talked about buffers. And buffers are when I have a weak acid and a weak base. So let's say we have these three solutions, HCl and Cl minus. Is that a buffer? No. Why? Because HCl is a strong acid. How about B? Well, I have NH4 plus, that's weak acid, and HF, that's a weak base. But notice they're not connected. These two have to be a pair. Okay, so this is not. But C is connected, right? Because if NH4 plus loses an H plus, I end up with NH3. So these are a weak base and a conjugate acid. So that is a buffer. All right, so the other thing we need to do is we need to remember what pKa is, and that's because we use it in our calculations. And pKa is the negative log of Ka. So if my Ka is 1.5 times 10 to the minus 5, I take the log of that, that gets me negative 4.8, and I change the sign on that, that's 4.8. Okay, so last time we went through buffers. We have this handy-dandy equation here called the Henderson-Hasselbalch equation. This equation basically lets us determine the pH for a buffer based on the Ka of the acid and the ratio of the base to the acid. Okay? And then we went through a problem of what happens if I add acid or base and see what the pH shift is. Okay? Remember, that's what buffers are. They resist changes in pH. That's why we care about them. And we use them, well, my body uses it because it's in my blood, right? My blood is a buffer. Okay, so let's say I have a buffer. I have a weak acid and I have a weak base. I have a pair. And all of a sudden I add in some H+. What happens is that H+, which is an acid, reacts with the base to form HA, the acid. If I added in instead OH minus, that's a base, it would react with the acid in my buffer. Okay? So basically, they work with each other to remove any extra added H plus or OH minus. Okay? So we went through and we figured out the pH of a buffer based on the moles or molarity of my base, or of my acid, and of my base, okay? And we use the Henderson-Hasselbalch equation. It makes life a lot easier. Then we went ahead and we said, what happens if I add an acid? If I add an acid like HCl, okay, what I can do is I can just figure out, using an ice chart, what happens to that acid. All that extra H plus goes away, and I'm left with still my weak base and my weak acid. Okay? All right, and then I can use the Henderson-Hasselbalch equation to figure out the new pH. Notice when I added in HCl, my pH lowered, but it didn't lower a lot. It lowered only a little bit. Okay? That's if I add an acid. If I add a base instead, what's going to happen? My pH is going to increase, but it's not going to increase a lot. Okay? All right, so I added in base, I added in OH minus, and so my OH minus is going to react with the acid. okay, to form this CH3CO2 minus. So again, I use something kind of like an ice table, not quite, because I'm not actually getting to equilibrium. And then I use Henderson-Hasselbalch, okay? All right, so that's a little bit of review. If you want, you can go back to the old lesson, go in, figure it out, because video problem 23A is all about using a buffer, right? So we're told we have a buffer here, acetic acid and acetate. We're given its Ka. We want to know its pH, and then the pH after I add an acid and after I add a base, okay? So go ahead, do this problem. We'll come back to it. Yeah? All right, but let's go back to the problems we did last time, right? We looked at what happened if I have a buffer at pH 4.74, and all of a sudden I go ahead and I add an acid or base. Well, we can ask the question, can I add too much? Is it possible to add too much? So let's say I have my buffer. My buffer has CH3, CO2H. Let's see, I have 0.1 molar and I have 100 mLs of that, so that's going to be 0.01 mole of my acid. I have the same amount of my base, that's the acetate. Okay. And all of a sudden, I'm going to add in some NaOH. Okay. Now, I add in 0.01 liters of 2 molar OH minus. So that's going to get me 0.02 mole of my OH minus. Okay, so my OH minus is going to react with one of these two. The key thing is I always have to go ahead and I need to think, this is a base, what's it going to react with? Is it going to react with this acid or the base? Well, acids react with bases. Bases don't react with bases. Acids don't react with acids. This is going to react with my acid. So I'm going to have my CH3, CO2H, plus my OH minus goes to form CH3, CO2 minus. Okay? All right, so initially, I have 0.01 mole. I have 0.01 mole because I have a buffer, and I'm going to add in 0.02 moles. Okay. Now, if we look at the previous problems, the thing with buffers is they always remove all of the OH minus. Well, in this case, I can't remove all of that because in order for 0.02 moles of this react, I need to have 0.02 moles of this, but I don't. So only 0.01 mole of my CH3CO2H minus reacts. Why? Because this is my limiting reactant. Uh-oh, that's a 215 term. Remember, limiting reactants, they're the ones that limit the reaction. So this is going to increase by that amount. So then, finally, I'm going to get 0 of this. I'm going to get 0.01 mole of OH minus. And I'm going to end up with 0.02 mole of my CH3CO2 minus. Okay. Now, in the previous problems, what did I do next? Next, I would go ahead and I use Henderson-Hasselbalch equation. But Henderson-Hasselbalch equation only works if I have a buffer. Do I have a buffer anymore? No. I have 0 moles of my weak acid. So I no longer have a buffer. Instead, what I have is I have some leftover OH minus. So I could actually go ahead and I could figure out that I have 0.01 mole OH minus. My new volume is I have 100 mLs, and then I added in 10 mLs, so that's 0.11 liters. That's 0.0909 mole per liter OH minus. And I could go ahead and find pH because H plus equals 1 times 10 to the minus 14 over OH minus. That's 1.1 times 10 to the minus 13 molar H plus. I then take the log of that, and that gets me a pH of 12.9. Is this a buffer anymore? No, because notice my buffer originally had a pH of 4.74. Now it's 12.9. That's a huge difference in my pH. So it no longer is acting as a pH. Let's just show this on the screen. All right. So I go ahead, I figure out how much of everything reacts. I realize that, oh, my OH minus doesn't all go away, and I end up with a huge pH. This is no longer a buffer. And so the question that we asked at the beginning, can we add too much? Yes, we can. And this is called the buffer capacity. How much strong or acid or base can be added before the pH changes dramatically. Okay? Buffers can only resist so much acid or base. If I add in too much, it's going to start changing a lot. Okay, so what makes for a good buffer? Well, there are a few rules. Generally, when we want to do a buffer, we want to have an acid to base ratio of about 1:1, right? So about equal amounts of whatever my acid is and my base, okay? If I have dramatically less, if I add 0.1 to 1, so I add 10 times more of one, it would no longer be a buffer, okay? The second thing we want in buffers is we want the pKa to be close to the pH. The reason being is, if I add a ratio of 1:1 here, then my pH would equal pKa, because log of 1 equals 0. Okay? So I want to choose as my weak acid something with a pKa close to the pH. Okay? Actually, let's go ahead and have you guys figure out what the best use of this is. Which ones of these will be the best buffer, right? We have 0.01 molar. Oh, so best buffer at pH 9, right? So we want to make something that has a pH 9 and a buffer, okay? So we have 3 different pairs of acids and bases with different Kas and different ratios of those acids and bases. All right, this is video problem 23B. All right, the last thing we're going to talk about with buffers is why do we care? Why have I spent 1.5 lectures on buffers? The reason is they occur a lot in nature. We already talked about blood, right? My blood will always be a very similar pH. If it changed a lot, I would die. This means that if I go and I have a very alkaline diet, let's say something that is very basic, that's what alkaline means, okay? My blood isn't going to change pH much. It's going to stay fairly constant. Okay? We also have oceans. Oceans have a buffer also with H2CO3 and HCO3 minus. These come from 2 places. They come from CO2 in the atmosphere going ahead and dissolving in there to form the acid. And we have rocks and soils that dissolve to form carbonate. And so we have a buffer that involves an acid right here and its bases, right? This is a diprotic acid, so it produces 2 bases. Okay. Well, what's been happening? Well, over time, with climate change, we're producing more CO2. So over time, the amount of acid has been increasing. And notice if I increase the amount of acid in my buffer, what happens? My pH goes down. This is one of the side effects of climate change. Okay. We also use buffers a lot in chemistry. In labs, we do it to control reaction. We want a reaction to occur at a specific pH, so we use a buffer. Every once in a while, you hear shampoos where they say it's pH balanced. For instance, this shampoo, if I look at the ingredients, what do I see? I see I see citric acid right here, and I see sodium citrate. Okay, citric acid, that's this compound right here. This is citrate, and so what happens? I have a buffer between these two. All right, so that is it for buffers. Last lesson, we went through the first part where we talked about Henderson-Hasselbalch. Then we talked about shifting buffers, and then we talked about buffer design. Okay. Now we're going to shift, and we're going to talk about another type of neutralization reaction involving acids and bases. And this is a type of reaction that you did in lab last year, or last quarter, and you've been doing in labs this quarter, and that is called titration. Titration is one of those bedrock, everyone does it in chemistry, it's really important, okay? It's also important in biology and in a whole bunch of science, okay? So what is titration? Titration is using one solution to figure out the concentration of another solution, okay? So it's determining the concentration of a solution by having it react with a solution with a known concentration. So I have two solutions, they react. The one that we know its concentration is called a titrant. The one with the unknown concentration we call an analyte. Okay? Typically, the titrant is put in what's called a burette, which is a long tube that has volume markings on the side. And the analyte, the one we don't know the concentration of, we put in the flask. Okay? And then what happens is we add titrant to the analyte until we get, for acids and bases, to something called neutralization. And that is when we have equivalent amount of acid and base. Okay? This is called the equivalence point. The equivalence point is when I have the same amount of acid and base. All right, so when we're dealing with acids and bases, typically how we can measure the progress of this reaction is by reading the pH. Okay? And this is something called a titration curve. A titration curve is a measure of the pH of a solution as we add acid to base or as we add base to acid. Okay? We're going to go through 5 different titration curves. We're going to start off with strong acid, strong base, then strong base, strong acid. Then we're going to deal with weak acids and weak bases. And then finally, we'll talk about polyprotic. All right, but let's start easy. Let's say we have a strong acid and we're going to titrate it with a strong base. Okay? What this means is in my flask will be the strong acid. Okay? Typically this means I don't know its pH or its concentration. But in this case, let's say I do know its concentration. And then I'm going to add to it with a burette a strong base. Over here on the right, this is the pH curve we'll see. Notice the pH, we have pH versus the mLs of titrant added. When I've added 0 mLs, this is the starting point, okay? Notice, at the very beginning, I start off with acid. That's why my pH is very low. As I add base, my pH is going to increase, okay? And it goes through this curve here, right? In the first part, I have a lot more acid than base. Then I have a lot more base than acid. And right in the middle, that's where we have the equivalence point, okay? It's where the moles of acid equals the moles of base, okay? Looking at it in mathematical terms, this would be what we call an inflection point, right? Notice here, it's increasing in slope, and then it starts to decrease in slope, okay? That's an inflection point. The big thing is, if I look at this, okay, notice what's happening with the pH. When I go from 0 to 10 mLs, my pH is only changing from, let's say, 1 to 1.5. When I go from 10 to 20, my pH changes from 1.5 to 2. It's not changing a lot. But notice what happens right here. When I go from 22 to 25 to 27 mLs, my pH changes all the way from 2 to 12. So I have huge changes in my pH around this equivalence point. Okay? All right, let's go ahead and let's make a titration curve. All right, so let's say we're going to titrate 25 mLs of 0.1 molar HCl with 0.1 molar NaOH. Okay? That means in the flask, I'm going to start off with 25 mLs of 0.1 molar HCl. Seeing that it's 0.1 molar HCl, it produced 0.1 molar H+. I could then do negative log of 0.1, and I'd get a pH of 1.0. Okay, so that is my analyte. Okay, what am I going to add to it? I'm going to add in my titrant. Okay, so I'll fill this up with my NaOH. Okay, in this case, I'm adding base to acid. Okay, now I'm going to slowly add this in, and every once in a while figure out the pH. Okay. I can have a pH meter in here. Sometimes we actually figure out that equivalence point by indicator, right? Which is a color change indicator. But in this case, we're going to use a pH meter. Okay? So let's go ahead and let's try to figure out the pH when I've added in 10 mLs of my 0.1 molar NaOH. Okay? All right, so I start off with HCl. We know HCl is a strong acid. And then I add in NaOH. We know that NaOH is a strong base. So I'm going to take H plus and OH minus, and they're going to come together to form H2O. This is the reaction that occurs when I take a strong acid and mix it with a strong base. Okay? So what I'm going to do is, similar to what we did for buffers, I'm going to do something kind of like an ice table. All right, so let's figure out how many moles of each I have. Okay, so the amount of H plus I have, notice I have 0.1 molar H plus, and I have 25 mLs of that. So that's going to give me 0.0025 moles of my H plus. My OH minus, I have 0.1 molar of that, and it's 0.01 liters of that. And that's going to be, 0.001 moles of my OH minus. I don't care how much H2O I have. It's liquid, so it doesn't matter. Okay, so what's going to happen? Well, what's going to happen is all of one of these is going to react. Okay? Which one do I have less of? The OH minus. So this is my limiting reactant, so it's going to completely react. These are both reactants, so if OH minus decreases, H plus decreases. So that's going to get me 0.0015 moles of H plus and no OH minus. Okay? Now in reality, it will form a little bit of OH minus. I could find that by figuring out the concentration of this, then the concentration of this. But I can go ahead and take this divided by my volume. Notice that picture I have on the bottom right. I've taken my acid and I've added in base. So what's my new volume here? My new volume in there is 35 milliliters. Why? Because I start off with 25 milliliters and then I added in here 10 milliliters. Okay, so I go ahead and do that. That's going to get me my molarity, and from that I can find my pH. That's going to be 0.043 molar H plus. I take negative log of that, and that's going to get me 1.37. So my pH is now 1.37. Notice it started off at 1.00. So what happened? I added in pH, or I added in base, and my pH increased. All right, here's that calculation on the screen. Okay, I figure out how much H plus I have, how many moles of OH minus, and then I let them react according to this equation. Okay. All right, so that found my excess H plus, and from that I can figure out my molarity H plus and then my pH. Okay. All right, now let's go ahead and let's do another one. Let's say we have 20 mLs of 0.1 molar NaOH. Right? So I start off with 10 mLs. Now I'm at 20 mLs. So now I have 45 mLs total. Okay? So I want to now know what my pH is. So I'm going to do this same exact thing, except now when I add 10 mLs of NaOH, I add 0.001 moles. Now I have 0.002 moles. Okay? So I put that into my ice table. I started off with 0.0025 moles of H plus. I have 0.0020 moles of the OH minus. I still have more H plus than OH minus, so all my OH minus reacts, and I still have some leftover H plus. Okay. Now I go ahead, now that I know how much excess H plus I have, I divide by my volume, which is 45 ml, and that's going to get me my molarity. In this case, 0.011 molar. Okay. I can figure out the pH of this, and that's going to get me 1.95 for my pH. Okay. So my pH went from 1 to 1.37 to 1.95. Notice it's increasing. Why is it increasing? It's increasing because at each step I get more and more OH minus on that. Let's do this one step further. And let's say now I get to the point where I have 30 mLs of my 0.01 molar. Now, I still had 0.0025 moles H plus, but now I have 0.0030 moles OH minus. So now, which one is my limiting reactant? In this case, now, my H plus is my limiting reactant. Okay? So what's going to happen is, now all my H plus is going to react. And I'm going to end up with excess of my OH minus. I didn't do this in an ice table, but I could do it the exact same way. Okay? I then take my moles OH minus, I divide by the new volume, which is 25 plus 30 mLs. Okay? I get my molarity of OH minus. I can then use that to figure out my molarity of H plus, and from that I can get my pH. In this case, it's 12.0. So notice what happened. I went from having here excess H plus, and that's why my pHs are very low, to now I have excess OH minus. So now my pH ends up being really high. I could do the same math for 40 mLs. I'd get a pH of 12.4 for my pH. And I could actually get even more data, and I'd get something that looks like this. This is a pH curve. And right here is my equivalence point. It's the point where my acid and my base are equal, right? Here, on this side I have too much acid. On this side I have too much base. Right here, I have equal amounts of acid and base. Okay? And this is the key to titration curves. Okay? All right, so notice that the pH at that equivalence point is 7. Okay? That is what happens when I have strong acid with strong base. Okay? Let's look at the opposite way. If instead I had a strong base and added in strong acid, in this case, my analyte would be base, and I'm adding in acid. So seeing that I'm adding acid, my pH decreases. Notice how this is just the opposite. I've just flipped the two equations, right? I just flipped the two graphs. My pH is still at 7, but now I'm going from a basic pH to acidic pH. Okay. All right, so these are two titration curves for having strong acid and strong base. Okay, they differ based on which one I'm adding to the other. Okay? Let's now actually use a pH curve for what we want to do, right? Why do we do pH curves? We do titration in order to figure out the pH or the concentration of one mineral. All right, so let's say we have 125 mLs of NaOH, and I titrate that with 0.018 molar HCl. Okay. We have this curve. You see it better on the thing where this is ml, this is pH. Okay, and we want to go ahead and we want to answer these questions. Okay. All right. So the first question is, what's my analyte and what's my titrant? All right. If you go back to the very beginning of this section, I said the analyte is always the thing I don't know its concentration. Well, I know the concentration of this, so that means NaOH must be my analyte. HCl, I know its concentration, so that makes it the titrant. Okay? It also happens, the analyte is what I start with, okay? Notice at the very beginning I have a high pH. So if I have a high pH, that means my analyte must be a base. Okay, in this case, NaOH. All right, B. Sketch out the setup. Okay, so what does this mean? Well, every titration looks kind of like this. But the key thing is, that's an ugly beaker, Erlenmeyer flask. All right, that's slightly better. What's up here and what's down there? Okay. Well, I always put my titrant in the burette. And down here, this is where I'm going to have my NaOH. Okay? We always add the titrant to the analyte. Okay? All right. So that's over there. B. Let's get into C. All right. At what volume is the equivalence point found? That's where I use this curve. Okay, now in reality I can't know exactly where that is, but if I look here, here's 20, here's 30. So at what volume is this equivalence point? Well, it looks to be pretty much exactly between the two, 25 mLs. If you said 24 or 26, that'd be fine. But we're going to go with 25 mLs. All right, and now D. D is the real reason why we're doing it. What is the concentration of the NaOH? So the concentration of the NaOH is found by using that equivalence point. Okay? Now remember that moles H plus equals moles OH minus. Okay? That's what we said at that equivalence point. Nowhere else. Outside of that, I either have too much OH minus or I have too much H plus. But right here, I have moles H plus equals moles OH minus. Okay? So, I don't know how many moles OH minus I have, but I do know how much moles H plus I have. Why? Because I have a concentration and I have a volume. Always make sure you know what that volume refers to. This is the HCl. All right, so that's going to get me my moles of H plus 4.5 moles H plus. Okay. Seeing that I now know that H plus right here, I also know the moles OH minus. Okay. And now, if I know the moles OH minus, okay, and I take that and I divide by the liters, okay, that's going to go ahead and that's going to get me my molarity. Okay. All right, now here's the one thing, one trick from differently. This is the concentration of my NaOH. Okay. So I don't use the total number of liters, I just want the liters of my NaOH. So in this case, it's 0.125. Okay. All right, so when I do this, 0.00045 divided by 0.125, that's going to get me 0.0036 molar. That's for my NaOH. Okay. Let's show this on the screen. Okay. The key is to remember what that equivalence point. It means my moles H plus equals my moles OH minus. So I can figure out moles H plus. That's going to give me my moles OH minus, and then I divide by the volume of that base to figure out the concentration. All right, let's have you guys do a similar problem, but now we have a strong acid, 2.035 grams, and we're going to put that in water to form 100 mLs of acid, and we're going to titrate it with 1 molar NaOH. Okay, and we're told the equivalence point equals 32.3 mLs. Okay, so go ahead, figure out the moles of acid, the concentration of the acid, okay, and then also the molar mass of the acid. Okay, one key thing is, remember, we have molar and mLs. This is going to be of my NaOH. Okay, so I can use these two to figure out the moles OH minus. And now if I know the moles of OH minus, I know the moles acid. Okay? If I know the moles acid and the volume, I can figure out concentration. Molar mass is grams over mLs. So grams per mole. I know grams. I found moles, so I can find grams per mole. And then I want to draw a sketch of the titration curve. pH versus ml. Go ahead and sketch that out. All right, so that's it for lesson 23. Lesson 23, the last part is about titrations. We've looked at two different types. We've talked about strong acids with strong bases and strong bases with strong acids. These both have very similar reactions, and for both these the equivalence point is 7. It's just whether it goes up or down. This is for number 1, this is for number 2. Okay. All right, next time we're going to go ahead and we're going to look at weak acids and bases and then polyprotic acids. Okay, so that's it for this lesson. Remember, this has a short time frame. Homework number 23 is due June 3rd at midnight. And if you are seeing this before the test, remember June 1st on Saturday. All right, bye-bye.